But I have a question for you then.
Sorry.
If
Before
you
you do,
have a
why is that in the
100-meter
calculator?
tall building,
Why isn't that in the calculator?
it's generally not needed.
Sorry, you've just explained that stuff disappears with distance based on its angular size, and now you're saying it's not needed. The calculator will simply assert that it's Earth curve that's causing it. Well, it's not.
It is.
The angular size is causing it. You've just made that clear. Calculable in the Rayleigh criterion. And it's not included because it's not needed.
Nathan,
It is needed, and you're talking over me. I'll just shut you up. Yeah, this that he's now going to argue the toss about Ranty about isn't included in the curve calculator. So anything that disappears with distance, according to the curve calculator, the only cause, the single cause, is Earth curve. Sod all to do with what he's now about to argue with Ranty about. It's not included and not needed according to him, even though it's very real and how we see things.
It has nothing to do with it. And
sorry, I'll just do it again. This tree on screen takes up 50% of the frame, and I absolutely guarantee if it was 1,000 miles away you would not see it because it was too small. The calculator would say sod all to do with how small it is and only Earth curve obstruction. Well, that's simply not the case.
Correct.
Things get too small. Not correct. Things get too small to see regardless of your fundy belief in Earth curve. So, yeah, there are multiple reasons why things can disappear into the distance, and you can only claim Earth curve obscures them. Wrong. Things can get too small, and you can't resolve them. Nothing to do with Earth curve, completely ignored in your calculator.
Let's look at another example of diffraction limit. The lid in this example in a warehouse is marked at 1-inch intervals. The observer height is 1.5 inches. The pictures are taken at 20-foot intervals. So this is a fixed height changing distance example as opposed to a fixed distance changing height example. Again, video link in the description. So taking still shots of the video capture here, or the picture capture, we have 100 feet, 140 feet, 180 feet, and so on all the way to 460 feet. And you can pull these objects out and compare them to one another between the 460 feet and 100 feet, which there is very little to no angular resolution loss at 100 feet. And so if you overlap the two with the scaled paper of 1-inch intervals in between them, and mark out the horizon line as the point of the inferior miraging effect, then you can see that you have lost approximately 1.75 inches at 465 feet. And again, we can use this to then calculate theta for this particular wavelength, diameter, aperture camera. So we'll do that here. So again, this 1.75 inches is lost at 460 feet. So we plug in 1.75 inches as our height, which is 0.1458 feet across a distance of 460 feet. Using our same diagram as we've done before, solving for theta gives us a very similar angle to what we've gotten before, which is 0.018 degrees, very close to our 0.02 degree 1 arc minute human eye resolution limit. So using the loss to calculate theta for this camera within these conditions, I can now calculate the amount of loss over any distance. Alternatively, I can calculate the amount that is resolved with a change in height, just like we did before. So plugging in at 260 feet, I would expect a loss of about 1 inch. At 380 feet, I would expect a loss of 1.43 inches, and so on. If theta is held constant across any similar triangle, we can restate our formula as h1 over h2 equals d1 over d2, right? And as those ratios then could correspond to one another across tangent theta, as h1 over d1 equal to h2 over d2. So if you know the distance to an object and the amount that is lost across theta, you can calculate when the object would be completely lost. So for us, our 11.5 inch height lid completely disappears over the horizon at a distance of 3,050 feet, or 0.57, half a mile, give or take. Alternatively, over a distance d of 1 mile, 5,280 feet, we would lose a height of 1.65 feet, or 20 inches. Of note, if this lid were instead a 6-foot man, he would disappear at 3.6 miles within these wavelength and aperture conditions. Again, this is an optical phenomenon, it's not physical curvature. The lower horizon limit has been met, the compression rate has been met below the eye line, or below the aperture, or below the eye line of the camera in this case. And so the upper aspect with distance is going to set into that line. As another example, you can see the effect more clearly here. The lid is marked at 1 inch increments, and the photographed is then photographed 1.5 inches off the ground at various distances away. So some of the pics were downloaded at different levels of zoom, but you can see the effect on the lid. It disappears into the floor and the whole lid is brought downward. You can see the lines on the lid gradually merge with the floor, and I've outlined those markings and placed them against the purple line. You can see that you start to lose them all sequentially as with greater distance. So let's summarize where we've been up to this point. I want to impart to you that the loss of information at our horizon is an optical phenomenon. The ground is brought to eye level. Our eyes are not brought to ground level. Distant objects disappear by a combination of the angular resolution limit of the observer and upward refraction phenomenon. So option 1, again, the ground is brought to your eye level. The person disappears from perspective by walking straight away and vanishing bottom first from things getting smaller with distance and an angular resolution limit. And here's some of the examples that we've gone through to this point. We have our lid disappearing into the floor. We have some calculations that we can use to determine our horizon distance and or loss rate with height change. So for example, at 100 miles, we expect to lose roughly 184 feet by angular resolution at 0.02 degrees. But with curvature at 100 miles, we're losing 6,660 feet. So the takeaway is that with distance, diffraction plays less of a role than refraction does. That's the takeaway here, because we do see the bottoms of things lost at a greater rate than simply 184 feet at 100 miles. By extension, the use of infrared camera technology is very useful over long distances, since it is more prone to diffraction issues but experiences less refraction at the same time. So because refraction does play a decent sized role, that the infrared camera technology is proving to be a very good tool to view these distant objects, which again do not have anywhere near the expected rate of loss, such as 6,000 feet of loss at 100 miles. It just doesn't exist.
In this regular photo, you're able to see a lot of Clark Island, and you can see the green buoy channel marker on the left-hand side as well. And in this infrared photo from the same location, you're able to see better detail in the trees and the island itself. So infrared definitely makes a difference when it comes to showing detail when we compare these two images as seen here. Now, using an Earth curve calculator with an observer height of 17 feet and a target distance of 19.59 miles, we get a hidden target height of 141 feet. Now, as I stated before, the island has a maximum land height of 95 feet per Wikipedia, plus a maximum tree height of approximately 100 feet, and this is being generous for a tree height in the islands. So if we go worst case scenario, the island is approximately 195 feet tall at its highest point. If you look at the hidden target minus the maximum height of the island, including the trees, there would only be 55 feet of treetops that you would be seeing above the horizon as shown in my example here. Yet you can make out all the different types and shapes of trees and even what appears to be a rocky dark coastline of the island. Now let's take a look at Clark Island from Orcas Island looking west, and you'll notice the lower portion of the island between north and middle and how they compare to the infrared picture, and also notice the dark edge coastline. To me, this is clear evidence that there is no curve. The infrared image clearly shows the shape of the island, individual tree shapes and sizes, and even a rocky coastline. At a distance of 19.59 miles between the two locations, the globe map tells us 141 feet of the island should be hidden from view.
So our rate of curvature is 6 feet lost at 3 miles from a 6-foot observer height. We need to approximate the angular resolution limit line within our curve as close as possible. We only have 2 crossover points, one at 0 miles and one at 3 miles. We know that the size change must be exponential within perspective in order to get a curve to develop out of it. Can't be linear. So we will solve for the Earth's radius by knowing the arc length and arc angle. You can see here we've just taken our 2 triangles, placed them against a curve for a person walking over at that rate of 6-foot loss over 3 miles, and we have then extrapolated it along a greater circle. So the observer would assume they are watching a person descend from their point of view across 2 theta at 3 miles. The first theta, 0.0216 degrees, would represent the observer height at 6 feet until reaching 0 feet, and the second theta for the drop from 0 feet to minus 6 feet. So we can therefore take our arc angle of 2 theta across an arc length of 3 miles, or we can take the drop rate of 12 feet across 3 miles. Either will give us r for the greater circle. We can now solve for the radius of Earth from the angular resolution limit of the eye as our segment here with r along the radius or along the one aspect of the triangle and 3 miles as our opposite end, and the angle being across 2 theta, which is 0.0432 degrees. That will give us one number, and the alternative is to use the ratio of 12 foot over 3 miles is equal to 3 miles over r. Both will give us the numbers listed below, so we get for one number 3,978 miles, and for the other one 3,959 miles, giving us an average of 3,969 miles. So for our circle based on the angular resolution limit of the human eye, we can calculate a radius of 3,969 miles, and the circumference then comes out to 24,938 miles. And coincidentally or not, the Earth's radius is said to be 3,963 miles with a circumference of 24,900 miles. So for the information above my eye line, the descent rate is now steeper, just like with the bottles, but I have less of an angular compression rate, right? The angles are more open. So these angle pairs, the 8s or the 1s or the 11s, etc., must always remain in proportion, but diminish together according to the ceiling or floor distance. If one angle decreases, the other increases, but they are both diminishing with distance. Theta is never met along the top, again, because the horizon distance is set by the bottom. It occupies 50% of my vision, so wherever the information above my eye line is at that point, when these two halves collapse, is what I see above my eye line in my perspective. The top continues on independently, but you will never see the objects diminish in size and reach theta along the top because they will have already set into your lower horizon. They are gone to your vision. Note also the steeper descent rate at the top. The higher the ceiling, the steeper the descent rate within our perspective. This is how our brain interprets it. The nearest ceiling or floor sets our horizon. Similarly, the nearest wall would set the vertical vanishing line if we were up against a long wall, let's say. So if we collapse our our diagram here and we press the image downward and along the top and upward along the bottom to reach a essentially horizontal line. So you see that along the bottom, the angle 8 doesn't have to travel very far to get to the purple line, but the angle 8 above has to travel quite a bit more to do that. But essentially what you're left with is basically what we see in perspective as I've depicted here in the upper right. You have the larger angles, resolution angles along the top, and a steeper descent rate characterized by the orthogonal lines. And along the bottom, you have more compressed angles and those closer transversal lines and more stabilized or shallower orthogonal lines. You also have the object larger to start out with, but then gets rapidly smaller with distance because of the how close in proximity those transversal lines are. And along the top, you have the object start out smaller, but it remains relatively stable because the angular size compression rate is not as great. So the angles remain somewhat large as it descends away from you. And it maintains its relative size for the most part. And at the end, it will eventually set into the horizon. So as you probably have guessed, the sun is a practical example of this. The sun and moon set because they travel a short distance in a straight line along the very high upper boundary. If we extend our ceiling to a tremendous height, you see that the rate of differential angular compression between the floor and the apparent ceiling is large, and the descent rate steepens dramatically. So the object descends to the vanishing line rather quickly while maintaining a relatively constant resolution angle as it travels. It therefore does not experience an appreciable change in size. Once it hits the lower horizon, it sets. Again, this occurs without the object having to travel very far because it is so high up, and without an appreciable change in size. Stated another way, the higher something is, the less it changes in appearance. The distance it has to travel before it sets is dictated by how far we are seeing below the eye line, which is in most cases about 3 miles. This is for a diffraction limited system, but remember there are aberrations and refraction effects within the atmosphere that can alter the size of objects and distort them.
We are your eyes. We are your eyes. Our job's to see the world around you. Your most important sensory organ times 2. Let's take a look into your eye to see of what they are comprised. Then we'll learn about the roles that they do play.
Also, because Polaris is roughly 90 degrees above us at the North Pole, we can calculate, we can use it to estimate our latitude if we assume it has a fixed position. So if we use an astrolabe or a sextant and measure the angle between the horizon and Polaris, we will get our latitude. On a ball, it should be physically impossible to view Polaris beyond the northern hemisphere because you will have gone over the curve. They make it vast distances away so that they can assume the rays come in parallel with a tangent through the equator. No tangent exists in a straight line beyond 0 degrees at the equator though, because again, the rays are blocked by curvature. Polaris, however, can be seen as far away as 23.4 degrees south, which is the Tropic of Capricorn. So to make the math work, they tilted the Earth and the new equator became 66.6 degrees to Polaris. Now suddenly it was okay again for people to see it from 23.4 degrees south, as well as other celestial observations. So again, just in the top right, you can see at 90 degrees at the north, 90 degrees north, Polaris is directly above you. And as you move outward toward the equator, the angle changes such that where you view it becomes your latitude. And then on the bottom here, you can see how the tilt was manufactured to allow people at 23.4 degrees south to maintain a parallel ray profile to view Polaris. But an alternative explanation is that Polaris sets at 23.4 degrees south into the lower half of our visual field, which is set by theta. And it happens when we are approximately 7,824.6 miles south. And again, video links in the descriptions for that. So to do the math on that, assuming accurate latitude, each degree of latitude is 69 miles. So that makes Polaris at least 23.4 plus 90 times 69 equal to 7,824 miles away. Since it only makes a very brief appearance above the eye line or horizon at that point. So it also means we can see celestial bodies 7,800 miles away. So for a circle of diameter of about 15,600 miles across our visual field. So at the least, we know that is the limit to our diameter of vision across which we can observe celestial objects. And then just keep in mind the 23.4 degrees south is the Tropic of Capricorn, the 0 degree equator. Then you have the 23.4 degree north Tropic of Cancer, and so forth. Recall that Polaris, which is fixed in the sky, moves higher about 1 degree every 70 miles or so as we go north. They chose 69 miles. The alternative explanation is that if I move 70 miles closer to Polaris, it rises 1 degree within my perspective. But assuming that the Earth is curved and Polaris is fixed, if a person walks 23.4 degrees south to 90 degrees north, they would cover about 7,824.6 miles on a sphere. So if this represents 23.4 plus 90, or 113.4 degrees, then 0 to 90 degrees north would be about 6,210 miles, or 69 times 90. So you can see we've just taken this globe representation, they've tilted it to a fixed, unmoving Polaris, thinking themselves that they are moving across the Earth to keep the fixed object within view, going 1 degree every 69 miles. If we lift the arc off of the Earth, and we can kind of represent it here along a straight line, and we see that as we move south, we can, using a sextant and comparing the angle to the star with the horizon, we can get our latitude. We've already gone over that. But as we'll see, what's really happening is that instead of your vertical field of view being 65 to 68 degrees, they made it 66.6 degrees and failed to take into consideration an additional 23.4 degrees of vision that occurs within perspective. Intentional or not, without this additional distance, they had to tilt the Earth. So we'll explain that a little bit here. Looking at our corridor, our vertical field of view limit is here. Over on the left, you can see how the angles diverge and converge from the light source, and they are converging back on our lens. So think of this limit as a limit of lens convergence. So this limits the angle at which we can create an image above us or below us, looking straight on at the horizon. So when we collapse our corridor around this angle into our perspective, it becomes the closest angle to our eye. In other words, it's the closest angle with which we can view those paint stripes, essentially. We can drop a vertical line from the points where these two angles reach the ceiling and the floor, and again, it limits the distance along the floor or ceiling that something can be viewed above or below us. But again, on a straight line view, we can still see an additional 23.4 degrees further. So again, our paint our paint strips that are attached to the ceiling or floor may limit there, but looking straight on at an object, we still get an additional 23.4 degrees of vision. So if we're viewing a distant star, however, we're estimating its distance to our eye. So it's essentially our eye line if the object is setting far away, right? So it is taking into consideration that 23.4. So if I'm using a sextant to measure something and comparing the horizon and the object, I'm evaluating it according to these vertical angles until 65 to 68 degrees, which is a maximum. After this point, you must tilt your vision upward to view the object. But if I don't take into account the vertical field of view, I do not take this additional 23.4 into account. So I believe something is 90 degrees away when it's actually 90 plus 23.4 degrees away. If we use 66.6 as our vertical field of view above our eye line, an object along the ceiling would be a certain distance plus 23.4 degrees. Again, this represents the other angle of that right triangle. So this distance is what is ignored when viewing Polaris from 23.4 degrees south. So we'll assume the vertical field of view as 133.2, which is just 66.6 degrees split above your eye line, 66.6 below. We'll recall that when something is high up, we are essentially rotating these angles down within our perspective to our eye line as they approach theta and set into the lower eye line. Again, once theta is met, that sets the lower half of our visual field, and whatever is left above our eye line becomes the top 50%. So looking at our diagram, we can reverse it to fit within our corridor at the maximum height and distance at which it can be observed over here on the right. So we'll just flip our diagram, flip the star and the eye, and the height there represents the furthest distance and height it can be. So again, when rotated down, this is the furthest point along our horizon that we can see. As discussed, the line represents 90 degrees plus 23.4. So from the 0 point to 23.4 represents about 1,614 miles, 69 times 23.4. And from the 23.4 mark to our horizon line is the 90 basically the 90 line to Polaris, or 90 times 69, which is 6,210 miles. And adding them up gets us our 7,824.6 miles. As you can see on the lower left, we've kind of outlined how those distance relationships work themselves out. The red line represents that vertical line dropped along from that 6.6 degree triangle along 23.4 degrees, dropping it down perpendicular to the eye line. So if I believe I'm on a globe and 7,824.6 miles represents an arc length from 23.4 degrees to 90 degrees, and 6,210 represents an arc from 0 to 90, then if I multiply my quarter arc of 0 to 90 by 4, I get a circle with a circumference of 24,840 miles and a radius of 3,953 miles. Keep in mind the radius of Earth is 24,900 miles and a radius of 3,963 miles. So again, what they think is happening is up here on the right. What is really happening is that they are not taking into consideration that additional 23.4 degrees that is dropped from the vertical field of view to our eye line. So this is one way they use the optics of your eye to tell you that you live on a sphere. Of note, the implication when viewed correctly within perspective is that when viewing celestial objects, if we move 70 or 69 miles closer to something, our horizon opens up about 1 degree, or it moves along 1 degree within perspective. Put another way, if we stay fixed, we see an atmosphere with a radius of roughly 7,800 miles and a diameter of 15,600 miles.
So will we have a long, prolonged pause and then you ignoring exactly what I've just said and then claiming victimhood when I point out that you've ignored me for the third time?
No, I'm just giving you dead air time to give you a chance to think about it and reset a little bit. And
think
then
about what?
Get ready to listen.
Think about what? You've just immediately ignored all angular relationships and started using the feet and inches value, actual sizes. So are you going to address that or just have a long, prolonged silence and claim, I've got to think about something?
Yeah, I'm going to address it directly from angular perspective or angular size.
It's not included in the Earth curve maths. There is only one cause, Earth curve. So you saying you're going to address it, how the hell are you going to address Mick West and the Dizzy Hub and the Walter Bisling calculators that all exclude this? Are you going to magically undo that?
I'm going to show you why it isn't necessary, but
Oh, so we're not going to include it then. So we've immediately done the quick switcheroo, which is say that you're going to include it, and now we're going to detail why it's not included. It is absolutely required.
It is absolutely required.
We see in angular size.
We see in angular size.
The further something is, the smaller its angle, and the more likely it will eventually disappear from our view due to its angular size.
Due to its angular size.
Something that you are now going to try and attempt to dismiss. Has he just buggered off? Has he run away?
Yes, I think he dropped.
Yeah.
He had to go to work.
Oh, really? Yeah. At the point that I'm absolutely obliterating his argument because he can't include angular size. The calculator's hijacked perspective. So there's never going to reach a point where he says, okay, I'll do the angular size, making it seem to the audience like he's going to insert angular size and do the calculations using angular size. No, he'll do a load of angular size maths and then ignore them completely and go back to actual sizes. Sizes that don't change with distance. A 100-foot building will be a 100-foot building if it's in the near foreground and it's taking up the entire frame, or it's too far away to actually resolve it at all because the angular size is small. It'll still be a 100-foot building according to Bob, and that's how he'll run the maths, because that's what he needs. He needs the effects removing from the calculations. He'll just say the 100-foot is 100-foot, even if it's 1,000 miles away. That's what the trick is. Hijack perspective by using actual size when we see in angular size.
That's what the trick is. Hijack perspective by using actual size when we see in angular size.
Bye-bye, Bob. Total failure. I'm not going to let you deceive my audience.
Here's the thing, Nathan. The Rayleigh criterion is a limit where it no longer is able to be seen. So the human eye 0.02 degrees. However, there are the degrees beneath that, well, are the larger angles. Also, they're starting to break down because they're still not fully resolvable. So there's also an argument to say that the Rayleigh criterion at 0.02 is where the limit where you can't see it. But then you've got probably 0.5 of a degree where you've got all the other pixels intermingling with each other that make it all look fuzzy and disjointed, and you can't tell one thing from another. You can see it, but it's just a mush.
What does diffraction mean, Ranty?
You tell me, Nathan. You've been asked this question. This is quite funny.
Interference.
So you do have interference between the, between the pixels at the very small angles, and then the diffraction limit is where it can't be seen. So all this argument about, I know what you were saying, at 173 miles, 100 meters will be lost to diffraction. Yeah, because you won't be able to see it. But then you've probably got 300 or 400 meters above that where it's all just being disjointed and jumbled up. All the information is being scrambled, so you can't see it. It's like when we look across water and we see at the top of the water we see that dark band. It's like it's all disjointed and jumbled up. You know, there could be a lot of information in there and it can't distinguish from one thing to another.
Yes, distortion.
So yeah, so it's all right saying there's a diffraction limit, but then you've also got to take into account the diffraction build up to that. You know, there's a build up to it before it finally cuts off. So there's visible, then there's jumbled up and disjointed, and then there's the diffraction limit at 0.02.
So these are absolutely things that can cause stuff in the distance to disappear. Fact. Now, that fact is not included in the curve maths. There's only one cause, Earth curve. So where the case is that something has disappeared due to its angular limitation, it will only ever be called Earth curve. That in itself should tell you that it's a lie, when there's absolutely other factors that can cause things to disappear. Not to mention the fact that we point out that it's in side elevation, using actual sizes rather than angular resolution. It's just nonsense that's using perspective and the effects thereof to assert Earth curve where none exists.
and we don't live in that world.
We are your eyes. We are your eyes. Our job's to see the world.